Welcome to Calculus First Period with Bach. While I'm coaching tennis in the beautiful weather out here, you're stuck in my room doing derivatives. Have fun. Reminder, I tried to talk to you guys about this on Monday. I previewed a lot of what second derivative talks about, and it's curvature. First derivative, you guys are really good at that. First derivative is always about slope of the function. So if I have a negative first derivative, my slope is tending down for that place. I could have a 0 for a first derivative, and those are important places because that helps me find my maxes or my mins, but sometimes there's a saddle. And lastly, I can have a positive first derivative, which means my slope is going up. Now, second derivative does not talk about the slope, it talks about the curvature. And I'm going to try and do everything second derivative in green for you guys. So the second derivative, again, I could have a negative, I could have a 0, or I can have a positive. If you have a positive second derivative, that means you're concave up. This is concave up. If I have a negative, that's going to be concave down. And there's two ideas if your concavity is 0. I could have it just be a straight line where there's no curvature. But for us, mostly we're going to be dealing with inflection points. And that's when I go from concave up to concave down. Now, if you stare at that little S that I just drew, you can see the first half of it has this concave up idea. And you can see that the second half of it has this concave down idea. And right where they turn from red to black, that point there is an inflection point. And again, that's where my second derivative is 0. Kind of think about with a car, I'm turning left. If you look at this from the side, I'm turning left, and right at that inflection point, I turn the wheel back right. Anytime you turn the wheel, that's an inflection point, when you're turning your concavity from one bend to another bend. So the whole idea of first derivative is about slope. The whole idea about the second derivative is the curvature and how it bends. Reminder of the first derivative test. The key things to the first derivative are you're always trying to find your critical points. Those critical points are either my hots, you remember, where my first derivative equals 0, or I call them my tons, where my first derivative is undefined. And as long as you have one of those, we've been setting up boxes. And on my third row here, if this is my 0, if I have a negative and a plus, I just know that that went down, flat, up. I found a local min. And likewise, if it was plus and negative, I found a local max. But there's two other possible options. If I did a plus and a plus, that means I'm going up, flat, up. That guy's merely a saddle, which does not have a max or a min. And my other option is if I did down, 0, down, down, flat, down again, is another saddle. So the first derivative test is as long as you can find a critical point, if you check to the left and check to the right of that critical point, it helps you decide if you're a local max, local min, or a saddle. The second derivative test can help you find those maxes or mins a different way. So again, you still need to find your hot or your ton. where my first derivative equals 0, or my first derivative is undefined. But let me just draw you a local minimum, and let me draw you a local maximum, and kind of take a look at this. This guy's a minimum. What's its concavity? That's concave up. And this guy is a local maximum. And that means my concave is down. So the whole idea of the second derivative test to help you find a max or a min is, as long as you know where this occurs, we can look for a max or a min by the second derivative. So if I tell you, let's say, example, x equals 2, f prime of 2 equals 0. Okay? X is a critical point here. That means I could have a max, or I could have a min, or I could have a saddle. First derivative test, you would have to check just to the left of 2 and just to the right of 2. But the second derivative test, as long as I tell you what is the second derivative at 2, and let's say it is positive, well, if I'm a concave up, that means I just found you a minimum. And hopefully that makes sense. Let's take a look at an example, and you can figure it out from it. So if I do an example, and I just said f of x equals x squared minus 2x plus 8. You guys can already sense what this one is. It's a parabola, and it's a happy parabola, so it is going to be a minimum. But let me just show you with the second derivative test. I can do this. First derivative equals 2x minus 2. Set that equal to 0. When I solve, 2x equals 2, x equals 1. That's my critical point. Again, it could be a max, could be a min, could be a saddle. I don't know which one it is yet. But to find it, you have two options. The first derivative test would be, I'd have to set up my box. Let's see, x equals 1, and that slope was 0, and I need to check to the right or to the left. So, looking at this, if I plug in any number greater than 1, let's say 5, 2 times 5 is 10, minus 2 is a positive. Any number less than 1, try 0. 2 times 0 is 0, minus 2 is negative. So if I have that, I went down, flat, up, I have a minimum. Notice, again, I had to check to the left and to the right. The second derivative test is, as long as you can take the second derivative, which is really nice on this guy, it's just from here, just 2. What's that concavity everywhere? It's a positive concavity. That means everywhere this graph is concave up. So that means that at that point, I have a minimum. Now, the only flaw to the second derivative test is this. Oops, let me back up a page and create a new page for you guys. The only flaw to the second derivative test okay, if my first derivative at a point, let's call it c is 0, if my second derivative at c is positive, I have a min. If it's negative, I have a max. If it is 0 or undefined, you don't know. Use first derivative test. Okay, this is just the first part of the notes today. Now you can open up part 2 and we'll continue on. Thanks, guys.